was on the tip, and I don't remember, did they also do the little cutting of the tips and put little auger, or was that the next guy? That might have been the next guy. Next guy, was it Went? Oh, there's someone in between, like Boyson or something. What was,
two names, Boyson.
Boyson Jensen. So they took on this little study and put little mica, which is a rock basically, put little mica in between, and that blocked the usable compound. And then they put agar plates to keep your bacteria on. They put that in between, and diffusible substance went through. So they knew it was a diffusible substance. It was produced in the tip in the presence of light that resulted in the elongation of cells on the shade side of the whale. Right. By some mechanism we don't completely understand, the oxygen is transmitted to the shade side and then moves by polar oxygen transport down the coleoptile chute, causing those cells to increase by the acid growth hypothesis. And that's why you get the curvature, because the oxygen causes cells in the chute to expand, grow bigger in the presence of oxygen. Right. This is the exact opposite of what happens in the root. In the root, the oxygen that comes down to the root, if you turn a root that's not going down and you turn it sideways, the oxygen that comes from the shoot down to the root will get transmitted to the bottom side, and that will slow growth on the bottom side, and that will cause the curvature. So oxygen inhibits growth in the roots, but stimulates it in the shoots, which is partly why hormones are confusing, because they have different effects in different parts of the body, and at different concentrations, and in combination with different things.
And so what Went figured out, how does that?
I probably would not, and I doubt that Dr. Lewis would ask you a question where you had to it's not like a history class, we wouldn't ask you who did what and when kind of thing. Okay. But we would ask you questions like, how do they know it's diffusible? Or how do they know that light is the trigger? Or we'd ask you the science part of it, not the history part of it. If that's helpful.
Thank you.
What else do you want to know?
Can you go through the process of xylem, like forming xylem?
So the process of xylem movement, you mean, or transport? All right, so, well, what do you know about xylem transport, first of all? What kind of a pressure gradient? Positive pressure gradient? Negative pressure gradient? Negative. Okay, so negative pressure. What causes the negative pressure? Again. Yes. Actually, the water potential. What causes the water potential? Go farther. What else? What's that? Yeah, solutes don't end up being that big of a deal for xylem because they're pretty dilute. So it's mostly just the pressure that's causing water to move in the So what's causing, so is it a high water potential or a low water potential in the xylem?
Higher than the atmosphere.
So the water potential of the leaf is less negative than that of the atmosphere. What's causing the water to move up the xylem, for example?
Transpiration.
So, well, let's stick with water potential just for a second. Is the water potential more negative in the xylem at the top of the plant or at the bottom of the plant? It's more negative at the bottom of the plant. All right, how does transpiration fit into all this?
It creates more negative pressure, water pressure.
Why does it create a more negative pressure?
Because of the water film and all that with microfibrils.
Yeah, that's confusing. Give me a simpler explanation. You're not wrong, just explain it more simply.
Is it more negative at the bottom or the top?
The water potential is going to be more negative at the top of the plant.
Oh.
The tension is going to be higher, but the water potential is going to be more negative. Does that make sense? Tension is the negative water. So, Evan, I'm not going to let you off the hook. So what is transpiration again?
Like movement of water out of the cell of the leaves into the atmosphere.
So it's going to be going from, like, how does it move out? Leak out?
Evaporates.
Evaporate. So that means it goes from,
Evaporates out of the cell.
what is evaporation? Sorry. Liquid to gas. And it goes out of the cell and goes out of the plant, right? So it leaves. What happens if you're sucking water out of a glass with a straw? Does the level of the water go down? It does. I mean, the glass becomes more empty, right? The water is leaving the system, right? So how do you get attention? You get attention because the water is leaving the system. It's going. It's going out of the plant. That loss of water creates that tension that we're talking about. It's a suction. It's a vacuum, basically. So, gas molecules are leaving. That creates a vacuum almost, and that creates the tension. And that tension is what ends up pulling water up through the xylem. And does that answer your question? Other questions?
What's a cotyledon? I talk about it a lot, but I'm still not understanding.
Cotyledon,
Yeah.
Cotyledon, cotyledons.
Yeah.
So cotyledons are in seeds. They're called seed leaves. So they're typically storage structures in seeds. If you think of a bean seed, there's two halves of it. You can actually split it open. Basically what you're looking at are the two cotyledons in a bean seed that are full of starch in this storage unit of those seeds. Corn doesn't have they have a cotyledon, but they store their energy in the endosperm, and they only have one cotyledon because they're a monocot. Monocotyledon has one cotyledon, dicotyledons have two cotyledons. And in seeds that store their energy in the endosperm, the cotyledon ends up being sort of like a placenta. It transfers the energy from the endosperm to the embryo. And bean seeds, they start off with an endosperm, but early on in the development, all the energy goes into the cotyledons right away. And the endosperm more or less disappears. That's kind of more detailed than you need.
So it's just like a storage area?
Yes. For most seeds, it's a storage area.
Can you talk through phone loading? Like,
Can I what?
phone loading?
Foam loading?
Yeah, because I know it's a pressure gradient thing from the source. Is that to do with the source and the sink stuff? Or is it more about the rotational gradient going into the seed tube stuff?
So if I'm talking about flow of loading, I'm just talking about what's happening at the source. If I'm talking about flow of movement, then you're talking source to sink.
Okay.
So which do you want me to talk about?
The source. The
Okay.
railway.
So flow loading at the source. First off, so what are we loading? Sucrose. And where's the sucrose being, where's it coming from?
Leaves.
Sorry. What kind of cells?
How do you pronounce it?
Parenchyma? Parenchyma. But I like how you said it too. So parenchyma cells, like the palisade parenchyma or the spongy parenchyma, basically cells that do photosynthesis in the leaves will produce sucrose. That sucrose is at a high concentration when it's being produced in those cells, and so it diffuses away from those cells, okay? and it tends to diffuse, in this case, towards the phloem because the sucrose is going to be transported out of the phloem, so that kind of makes a gradient, a high concentration and a low concentration by the phloem because it's leaving all the time, right? So it diffuses towards the phloem, and it can diffuse in two different pathways, or the two different pathways. Symplastic and apoplastic. Which is the one that's in the cell? Symplastic. Where is the apoplastic? It's in the cell wall. Okay. There's different ways that sucrose can get into the phloem, both the symplastic pathway and the apoplastic pathway. You only had to learn about the apoplastic pathway. So as that sucrose diffuses from cell to cell and eventually goes into the cell wall or the apoplast, then what happens? How does it actually get into the phloem cells? The proton gradient. So how does the proton gradient get formed?
Hydrogen ions going, like with active transport to the higher concentration.
So the proton gradient, it's going to be formed where?
Cell wall.
In the cell wall. So ATP proton pumps will pump protons into the cell wall from the sieve tube space. So then it creates a low concentration in the sieve tube and a high concentration in the cell wall. And then what happens? That proton concentration will be used to do what? Bring sucrose in using what specifically?
Co-transport protein.
A co-transport protein. So there's a co-transport protein that binds both protons and the sucrose. It takes the protons from a high concentration to a low, and it takes the sucrose from a low to a high inside the sieve tube cell. And that's how it pushes sucrose against its concentration.
When the hydrogen is being transferred to the ATP, is that primary active transfer?
Yes,
Is that in the
correct.
And then why was it already high concentration of sucrose in the phloem?
It's sort of a chicken and egg kind of thing a little bit. It's so at least during the daytime. So if you think about it in the morning, as the sucrose concentration starts to build up as the leaf starts doing photosynthesis, it'll diffuse towards the phloem, and the proton pumps will start to pump protons into the cell wall, and then that'll start to move sucrose in. So it doesn't initially start out high, but pretty rapidly you're going to get a fairly high concentration in the sieve tube cell. And then throughout the day it's going to stay pretty high because as sucrose is formed, it's going to be pumped into the phloem, and there'll be a continuous stream of phloem moving that sucrose away from the source.
So water follows the sucrose into the phloem.
Right, so once the sucrose is being loaded in, that decreases the water potential, the solute and the total water potential of the phloem, and water will come in, will diffuse in from the surrounding tissues in response to that. And that will create a pressure, a hydrostatic or water pressure, and that water pressure will move the sucrose and the sap, basically, the sucrose and the water from a high pressure to a low pressure. And at some place where the sucrose is being taken out of the phloem, that creates a low pressure, and that gradient just keeps the movement towards that low pressure. And that's the movement part of the
Can you go through development of male and female neophytes?
Sure. So male neophyte first. So this is going to be within the anther, which is the male flower part, the male structure of the flower. And there's certain structures. So if you actually do a cross section through the stamen, which is the top part of the anther, there's actually on most of them 4 different what we call pollen sacs, which are openings that have microsporocytes. Microsporocyte is just a diploid cell that's going to undergo meiosis. So sporocytes means it produces cell that produces spores, and microsporocyte indicates that it's the male part. So these cells undergo meiosis, and they produce, each one produces 4 haploid microspores. And each of those microspores divides once to produce a 2-cell pollen grain. And then those pollen grains get released and land on the stigma, and there's a sperm cell and a tube cell or generative cell. The sperm cell divides one more time, so then you end up with a 3-cell microgametophyte. All right, so for the female gametophyte, we're inside the ovary, and there's a structure in there called the embryo sac, basically. And within that embryo sac, there is a megasporocyte. So mega female sporocyte, spore-producing cell that undergoes meiosis. It produces 4 haploid cells. 3 of them disintegrate. One turns into, one of them divides several times to produce the female gametophyte. And the female gametophyte consists of an egg cell, a polar nuclei cell, which is 1 cell but 2 nuclei, 3 antipodal cells, which we really don't know what they do, and 2 synergids, which seem to be important in attracting the pollen to the micropyle, which is the opening through which the sperm gets injected.
So it says there's 4 microsporocytes. Does that create 16 microsporocytes?
So there's within a pollen grain, or within one of those pollen sacs, there's dozens, hundreds of microsporocytes. So you end up with a bazillion, but a whole lot of pollen grains.
So we're only focusing, we're following 1.
If we just follow one microsporocyte will produce 4 microspores. Each one will produce a pollen grain.
Okay.
Can you talk about the difference between the primary meristem and secondary meristem?
So primary meristems are at the tips of roots and stems, and they do what is called primary growth. And primary growth it's actually 3 parts of the meristem. One part produces ground tissue, one part produces dermal tissue on the outside of the plant, and the other one produces vascular tissue, the xylem and the phloem. And so when you have primary growth, you just have the elongation of a stem or a root producing those 3 tissue layers within, that material that's produced. Within most plants, particularly plants that live more than 1 year, you also have the potential for what's called lateral growth, which is the thickening of plants. And there's a ring around, and this is most easy to see in like trees, right? So you've got your pith in the middle, you've got xylem, and each year's worth of xylem radiating out. And at the very end of the xylem, there is a layer called a cambium, vascular cambium, which produces xylem on the inside and phloem on the outside of it. And that produces this thickening. Every year it produces a new layer of xylem, so the stem actually gets bigger.
This was procambium?
Would be the meristematic region within the apical meristems that produces
Around the vascular?
the vascular.
And then, so is.
You don't need to know that.
Okay. Secondary meristem, then like cambium would be within a secondary meristem structure?
Sorry, say that one more time.
So the cambium for,
The vascular cambium, like in a tree?
yeah, is that a secondary meristem structure?
Yes. So rather than elongating the stem, it produces girth.
Okay.
And there's a couple of different types. We only looked at one. So the only vascular cambium type that we look at, or really the only lateral meristem that we looked at, was the one that produces xylem on the inside and phloem on the outside. It's kind of cool. It somehow knows how to produce xylem on the inside and phloem on the outside, and I'm not sure how it does that. But the cells divide, and if it's inside of a layer, it's xylem, and if it divides with the derivative cell to the outside, it turns into phloem.